Thorben, I think you should be ready to share screen when you're ready.
Yeah, hi. Can I start, or should I wait, or is...
Let's see. I guess, yeah, we'll move right in. So, it's my pleasure to announce our next speaker for today, Thorben Kastenholz, who's going to be telling us about simplicial volume of total spaces of fiber bundles.
Yeah. Hi. Thanks, first of all, for the opportunity to talk about my research here. So most of what I'm going to say is joint work with Jens Reinhold, and it's about a paper from last year. But there's also some new stuff towards the end that I did on my own. So let's start by defining what the simplicial volume actually is. And for that, like, I will always use R coefficients. You can do a lot of this stuff integrally, but then it's way more confusing, and there's basically, as far as I know, nothing really known about this. So everything is here with real coefficients. And then if I have a singular chain, so it's just a sum of simplices, I can consider the one norm. So in this case, just the sum of the absolute value of the coefficients. And this gives me, well, as the name L1 norm suggests, a norm on the singular chains. And now for a homology class, I can take the infimum over the L1 norm of all its representatives and call this the L1 norm of the homology class. So conceptually, this is really just like the minimal number of simplices I need to represent my homology class. Note here, this is really an infimum and not just a minimum. So, for example, quite famously and quite often it happens that the simplicial volume of certain classes vanishes. So it's 0, but of course, every representative has positive norm. So this is really just a pseudo norm on a semi-norm on homology instead of just an actual norm. And now we define the simplicial volume for a closed, oriented, and connected manifold as the L1 norm of the fundamental class. So again, conceptually, this is the minimal number of simplices I need to, well, homologically triangulate my manifold. And the simplicial volume has a lot of properties that make it interesting for me, who would call himself a topologist and not really a geometer. So first of all, the simplicial volume is a homotopy invariant, which of course is quite different from the actual volume. And the other point is that if I have a homology class alpha and I look at its norm, then and I look at an induced map, then the induced map can only lower the the volume of a class, the L1 norm of a class. Because of course, whenever I have a representative of alpha, I can just push it through F to get a representative of F lower star of alpha. But there's a famous theorem by Gromov which says that if my map happens to induce an isomorphism on fundamental groups, or more strongly, if it is surjective and has a amenable kernel, then the map actually preserves the L1 norm. And in general, the simplicial volume is basically impossible to compute. You can even make this statement more precise. But the cool thing is that at least for, say, hyperbolic manifolds, you can compute the simplicial volume because it's basically just the actual volume of the hyperbolic manifold. So the quotient of the simplicial volume and the volume only depends on the dimension. And this is just the volume of an ideal simplex. And moreover, this quotient here between the simplicial volume and the volume of a manifold is always a constant that only depends on the isotopy type of the universal covering of the Riemannian manifold. So in a sense, and this is a theorem by Gromov and Thurston, like separately, and this hints at a very, very strong connection between the simplicial volume and the actual volume. But let's not focus on that, but let's rather get back to this statement here, because it has an interesting implication, namely, if the simplicial volume of my class is non-zero, of the manifold is non-zero, then necessarily the image of the fundamental class in the group homology of the fundamental group has to be non-zero, because of course the map from our manifold to the classifying space of its fundamental group is just the map classifying the universal covering. Because of course the map from M to B pi 1 of M is an isomorphism on pi 1, so it preserves the L1 norm, and the zero class has norm 0. So this gives us one motivation for the following definition, which is we call a manifold, well, rationally or just integrally essential if the image of the fundamental class in the homology of the fundamental group is non-zero, and otherwise we call it rationally or integrally inessential. And if the fundamental group happens to be word hyperbolic, then the simplicial volume being non-zero is actually equivalent to being rationally inessential, rationally essential. Sorry. So in that case, again, there's a stronger connection between these two notions. And so, before I can tell you about our results, let me maybe do something, a little bit of motivation first. So let's say we have a fiber bundle F to E to B, where F is not a point, so it's not really a trivial bundle, like a very, very trivial bundle, not like a product, but where the fundamental group of the fiber is amenable. Then the map from E to B is surjective on pi 1, and it has a amenable kernel, namely pi 1 of F, or a quotient of pi 1 of F. So the simplicial volume of E is the same as the simplicial volume of the projection of the fundamental class, which of course is 0. So in that case, the simplicial volume of the total space vanishes. This is like a very classical result. And moreover, if pi 1 of the fiber is actually 0, so a little bit, which is of course stronger than being amenable, then the total space is also inessential because the because the map from E to B pi 1 of E factorizes through B. Because the map to B is an isomorphism of pi 1 in that case. And so what Jens and I asked ourselves is, okay, what happens if we turn this around? So suppose we have a bundle, again, where F is connected and not a point, and the fundamental group of the base is now amenable or even 0, does the simplicial volume of the total space actually have to vanish? And moreover, is E even rationally inessential? And a little bit more specifically, what happens if the base is a sphere, which is of course the easiest simply connected manifold, or the easiest manifold one can think of with amenable or 0 fundamental group. And first of all, there's a counterexample if one considers the base to be S1, namely there are hyperbolic free manifolds that fiber over the circle. And of course, as I mentioned before, if I have a hyperbolic manifold, then the simplicial volume is actually non-zero because the actual volume is non-zero, and there was this quotient thing. So the next question we asked ourselves was then, okay, so if it can be non-zero, if it fibers over S1, what are actually the possible values if I fiber over S1? And here's this rather lengthy theorem, which says that if I have a finitely presented group, and I have some index which is bigger or equal than 7, and I have a homology class in the group homology with the corresponding degree, which is representable by manifold, meaning that there's actually a map from a manifold to BG, which maps the fundamental class to alpha, then there exists an inessential manifold S of dimension 1 less, which has fundamental group G, and a pointed orientation preserving diffeomorphism that also acts as the identity on the fundamental group. And then such that the map from the mapping torus, which is T phi, which is of course nothing but a space that fibers over S1, to BG times Z, which projects to BG, maps the fundamental class of this mapping torus to alpha. So to sum this up, every homology class in odd degrees bigger or equal than 7 has a multiple that is representable by mapping torus. Because by an old result by Tom, every homology class has a multiple that is representable by a manifold. And this has an interesting consequence because the projection from G times Z to G has a amenable kernel. And so the L1 norm of all homology classes is preserved. And of course, since this map here from the mapping torus to BG maps the fundamental class to alpha, and by the previously stated result, this means this map preserves the L1 norm, we get that the simplicial volume of the mapping torus agrees with the L1 norm of alpha. So to sum this up, we get that for every odd number bigger or equal than 7, every number that is realized as the simplicial volume of a 2m+1 dimensional manifold is also realized as the simplicial volume of a mapping torus. And moreover, the fiber of the mapping torus can be chosen to be inessential, and the diffeomorphism can be chosen to act as the identity on the fundamental group. And this is, at least to me, quite surprising, because the general theme is that the simplicial volume and its cousin bounded cohomology only see the fundamental group. And it's somehow always tied to the fundamental group, and everything else is somehow not relevant for the simplicial volume or the bounded cohomology. But here in this case, we have now a mapping torus where the fiber is inessential, so it is somehow not seen by the fundamental group. And the diffeomorphism acts as the identity on the fundamental group. And so it somehow also doesn't contribute to the fundamental group again. But somehow, if we consider the twisted mapping torus we get using this diffeomorphism, we get something interesting in fundamental groups. And so somehow to answer the question I asked before, there's a result by Clara Löh and Nikolaus Heuer, which says that the possible values of the simplicial volume are dense in the positive real numbers if the dimension is greater or equal than 4. So this somehow answers the base S1 case. So then the question Jens and I asked afterwards was quite obvious. So what happens if we are in the case where we look at Sn, where this here is now simply connected? And in that case, we get that the simplicial volume always vanishes. And the proof is based on the following idea, where we somehow consider the degree D map, self-map from the sphere to itself. That's a self-map. And we can pull back the total space of our, we can pull back the bundle along this map. And the corresponding map here from F upper star D E to E has degree D as well. And in particular, we get that the simplicial volume of this pulled back bundle is greater or equal than D times the simplicial volume of E. And so now what we do is we explicitly construct representatives for the fundamental class of the total space of such a bundle. And this is defined in terms of the clutching function, such that all of these representatives have the same L1 norm. But of course, this immediately gives you like this inequality here. So if like the norm term on the left-hand side and on the right-hand side are actually the same, or like bounded by the same thing, then of course this can't be arbitrarily big, so the simplicial volume has to vanish. But now one can ask the stronger question, so if something fibers of a simply connected manifold, is it already rationally inessential? Where of course being rationally inessential is stronger than having vanishing simplicial volume. And here, first of all, the rationality is really important, because you can consider the following bundle, where you consider as a base the quaternionic projective space, and then you consider you consider the real projective space of lines in R8, or rather H squared. And then of course, whenever I have a line in R to the 8, I can consider its quaternionic span. So this gives me a map from RP7 to HP1. And the fiber is going to be RP3. And of course, RP7 is essential because the map from RP7 to RP infinity maps the fundamental class to something not zero. But S4, which is the same thing as HP1, is of course simply connected. So, but rationally, of course, the homology of RP infinity vanishes. So, of course, this is going to be rationally inessential. And the theorem we came up with is a bit more restrictive, but if we have a bundle here where now the fiber satisfies the Novikov conjecture and the base is too connected and flexible, where flexible here means that it has a self-map of non-trivial degree, so a self-map which has neither degree plus or minus 1 or 0, then E is already rationally inessential. So these were the answers that Jens and I came up with. And now I investigated this some more and somehow took a closer look at this proof here. And I somehow noticed that there was a main player here that could also be defined for bounded cohomology, namely the Gysin or Shriek or Umkehr map. This map has like a million names. Or wrong way map, which is defined as follows. So if I have a bundle F to E to B of oriented manifolds and the bundle is oriented and so on and so forth, then I get these wrong way maps here, which map now from homology of the base to the homology of the total space, but they somehow add the degree, the dimension of the fiber in the degree, and dually for cohomology. And I think the most enlightening definition is you take, so let's say for the homology one, I can take my homology class, I can take its Poincaré dual, this gives me a cohomology class, which I can pull back to the total space, and then I can take the Poincaré dual again. So this gives me exactly this difference in the degree here, and it gives me a mapping, because it's somehow like using the induced map in cohomology, so this gives me this wrong way map here. And in the RAM cohomology, this can also be defined in terms of fiber integration, where you somehow integrate over the fiber, as the name says. And so now what I came up with is, if we have a bundle whose structure group is the identity component of the diffeomorphism group, then whenever we have a bundle with this structure group, then you can actually define pi Shriek on L1 homology and on bounded and pi upper Shriek on L1 homology and pi lower Shriek on bounded cohomology. And additionally, you get these inequalities here for the norm of a homology class along this pi upper Shriek. And this has the following corollary, which is maybe a bit more intuitive and doesn't use this weird L1 homology and bounded cohomology, namely, if I have a bundle as above, then the simplicial volume of the total space is bounded by a constant which only depends on the dimension of the base times B plus F choose B times the simplicial volume of this alpha should be the fundamental, the simplicial volume of the base. Sorry, I just copied the one above. So alpha here, can you see my cursor? Hopefully you can see my cursor. So the alpha here in the corollary should be a B. So the simplicial volume of the total space is bounded by some constant times this binomial coefficient times the simplicial volume of B times the simplicial volume of F. So in particular, we get that if either B, the simplicial volume of B or the simplicial volume of F vanishes, then the simplicial volume of E vanishes as well. And of course, this is, for example, in stark contrast to what we had in the mapping torus case, where since the fiber was inessential, its simplicial volume was 0, while the total space had non-zero simplicial volume. And moreover, if the base happens to be simply connected, then you can always reduce the structure group to be the identity component of the diffeomorphism group. So in that case, you get that the simplicial volume of the total space always vanishes. So the simplicial volume gives an obstruction to fibering over something simply connected. And So this is somehow the answers I came up with. There's also a lower inequality one gets, namely if the dual fundamental class of the fiber extends to a cohomology class on the total space, where you now have no restrictions on the structure group, then one also gets these lower bounds here, where now the simplicial volume of the total space is bounded by the product of the simplicial volume of the base and the fiber. And this is, for example, always satisfied if the Euler characteristic of f of the fiber is non-zero. Because in that case, you can consider the vertical tangent bundle and its Euler class, which will always restrict to the Euler class of the fiber. And of course, if the Euler characteristic of the fiber is non-zero, then the Euler class is non-zero. So with these inequalities in mind, one can finally ask the following questions. So whenever I consider the product of two manifolds, I get this inequality here. So on the left-hand side, we get the product of the simplicial volume. And on the right-hand side, we get, again, this binomial coefficient times the product of the simplicial volumes. And the simplicial volume of the product always lies in between those. But here, this binomial coefficient just stems from the fact that whenever I take the product of two simplices and triangulate this, then I get this many simplices. So now one can ask the question, does the total space of a div0 bundle, so a bundle with structure group div0, actually satisfy the same inequality? So I got this lower inequality with this restriction where someone needed that the fiber has non-zero Euler characteristic. And on this right-hand side, I had this constant, which is a bit artificial. So I would guess that one can somehow get rid of this constant by just being more efficient in the construction of this map. And finally, one could ask the following question, namely, if the simplicial volume of such a bundle will always agree with the simplicial volume of the product. And the main reason why this might be true is that if you really look at my proofs, then you would see that there's really not that much going on for the simplicial volume. So there are many tricks one can do that somehow show that the representatives here of such a diversity of the total space can be chosen very nicely. But overall, I of course have no answer, otherwise it would be a question. And with that, I think I can finish a bit early.
Let's thank our speaker. It's right on time, perfect. Any questions for our speaker? Feel free to unmute yourself or put it in the chat. I just had a quick question about the simplicial volume 0 objects. So you have this one with the fiber over the sphere. Is there anything else you could like, these types of things will always have simplicial volume 0, or are they, if that happens, then like, you know, something nice about that, or is it just kind of another number to get?
So overall, I mean, I would say most obvious examples of vanishing simplicial volume are either manifolds that are flexible, so again, manifolds that have these degree D self-maps, or manifolds that have amenable fundamental group, or even fundamental group 0. And at least for these flexible manifolds, it's quite obvious what you can do, because now I can take a representative of the fundamental class of my manifold and push it through the degree D self-map. This gives me a representative of D times the fundamental class, which uses the same number of simplices as 1 times the fundamental class. So now I can take 1 over D times this representative, and this gives me like a sequence of representatives that converges to 0, whose norm converges to 0. And this is, I would say, the most obvious case where someone really see geometrically what is going on. And this somehow really work. I mean, in a sense, this fact and this construction, this degree D thing, really happens in this proof again. But apart from that, I would say that it's still very mysterious. There's, for example, a conjecture by Gromov which says that if I have an aspherical manifold, so a manifold with a contractible universal covering, which has vanishing simplicial volume, that this implies that the Euler characteristic is 0. And this is not known. And this, I think, hasn't been known for quite a while. So this is somewhat an old conjecture, I would say. And in general, I would say that the simplicial volume is still really, really mysterious. Especially, it isn't really computed that often. So of course, for hyperbolic manifolds, you get something. Then you get something for products of surfaces, but then that's almost it. So apart, of course, from these like these degrees, these simplicial volume 0 cases I mentioned. So there's still a lot to be learned about the simplicial volume, and also a lot to be computed, even though it is in general impossible to compute.
Interesting, thank you. Any other questions for our speaker?
Yeah, I would like to ask, why did you need the integer in your proof to be greater or equal than 7?
In where is it? This result, you mean?
Yeah.
So this proof uses something which is called the twisted double theorem, which says that whenever I have a manifold, I can somehow represent it as as I take two copies of the same manifold with boundary and glue them together along a weird diffeomorphism of the boundary. And this is only true for odd dimensional manifolds. So this is somewhere where this oddness comes from. And then you need the dimension to be big enough so that this whole stuff with the fundamental group works well enough. So now you have these manifolds with boundary where the boundary will have certain nice conditions in relation to the homotopy type of the whole manifold, and you need the codimension to be high enough of this boundary to make this work with the fundamental group. There's also a chance that this might work in dimension 5 as well, but if it would work, then it would be way more complicated. So there's also a result by Quinn about this twisted double theorem in dimension 5, but it's way more involved than the bigger equal than 7 case. So this is why we need this bigger equal than 7 thing.
Okay, thanks.
Great. Any other questions? Excellent. All right.